I'd like to thank everyone for coming over today in this bitter cold weather and attending this conference. It's my pleasure today to introduce Gil Alterovitz as our keynote speaker. Gil is an assistant professor at Boston Children's Hospital and Harvard Medical School. My alma mater for a few years before I switched to Genzyme as a medical director. And Gil is the director of the cybernetics laboratory and has been influential in the biomedical informatics literature for his work at that group. In addition to that, Gil has served as the chair of the HL7 clinical genomics work group, as well as he's also the chair of the EEE clinical genomics track that's going to be held in Cambridge later this year. So with that introduction, Gil, I'll go ahead and hand over the mic to you, and we're looking forward to your presentation.
Thank you very much, Sanjay, and everyone for having me. Yeah, my name is Gil Alterovitz, and I'm going to tell you guys today about some of the directions that I think big data and health informatics is going in general. And then I'll tell you about sort of an apps-based approach that I think would be useful thinking about this going into the future. So I think one place to kind of start is thinking about where all this data is coming from and what kind of data is specific to healthcare. So there's sort of several places where this data is coming from, and one of them is actually from Genomics. So here what we have is a plot that shows Moore's Law. How many of you guys have heard of Moore's Law? Well, that's great. So basically, as a quick recap, I mean, basically it actually relates to the number of transistors that are on a chip, and there was a saying that it would essentially double every couple of years, and the number that you could put on it, and therefore computational power would also increase in this exponential way. So if you graph things on a logarithmic plot, you'll essentially have a linear relationship there showing that exponential growth or the exponential decrease in cost. And what we've seen with sequencing in genomics, which is kind of where a lot of healthcare practice is going toward in the future, in terms of providing personalized care using your genetic information, that the costs are actually going down faster than would be predicted by Moore's Law. So it's actually kind of like a super Moore's Law, where it becomes even faster. So you can see that it started off, from 2001 or so to maybe 2008, approximately following Moore's Law. But beyond that, it actually, you can see here, that it actually exceeded, and it's now much faster. So if we look at kind of the other types of data that are being generated, we have them here. So here's Moore's Law, and as I mentioned, the amount of genomes that we're sequencing is going to be even faster than that. We have other pieces of information that are really growing rapidly. PubMed, the number of articles that are being published in the medical literature. At the same time, GenBank, which is related to the sequences of human DNA and other organisms that we know, is starting to saturate. So that means that essentially we're starting to get a much fuller picture of what it means to have a genome. So the Human Genome Project was officially completed quite a few years ago, but there's still been some development, but that's been saturated. So we're starting to know a lot more, and we're getting an explosion of new data from many different individuals, each of which have their own genetic information. So here, if we look at computational power, it's a little hard to see here, but basically these are different types of computers, and plotted, and you can see how fast they are in terms of MIPS, in terms of how fast they're able to process instructions, and then over the number of years. And you can see that this kind of extends that, essentially the computational power would be similar to that of like a mouse or so forth in maybe 20 or so years. We've already seen, and we'll see, we have a panelist from IBM Watson team, I believe, who's shown, a player that in jeopardy that's able to do pretty well. There's a number of other such things, but the main point of this slide is that it's growing really rapidly. And so the real secret is to merge the two, and that's kind of what we're going to see here, which is that healthcare kind of sits right here in the middle, in that it has a very large market, and it has a pretty good potential in terms of having a lot of big data, and we'll see a couple examples of that. On the other hand, until now, its historical growth has been relatively moderate compared to some of these other areas that have been using big data a lot more. So there's a lot of potential here. So that's kind of like what this slide is trying to show. And I want to go to the next slide to show you kind of how much data we're talking about here, at least in the US. So we're talking about approximately 50 petabytes of data. That's more than 100 times all of the data in the Library of Congress. So it's a lot of data, a couple of orders of magnitude more. And what kind of data, and this is just data in the healthcare realm that we think about traditionally, medical records, and now it's going to start to be genomic records and so forth. But there are other types of data as well. And there's certain characteristics of big data that I think are important to look at before we kind of figure out best ways to analyze it and best ways to approach it. And this slide kind of nicely summarizes that. So one thing is volume. So this is what most people think about big data, like a lot of it. But there are actually other things that are really relevant, and I'll show you examples of each of these when I show you about example applications. So having a lot of volume, large amount of data, that's kind of one thing that we'll see. But another thing is also velocity. So the data could be generated very quickly, and it may be in real time. So you can't just sit there and process something and then come back a day later, because by then you already have a bunch more data that you need to analyze. So you have to keep analyzing and giving results quickly. That's a feature of some types of data that we'll see in healthcare as well. And then another one is variety. So we have both structured and unstructured data that we'll see in healthcare. We'll see structured data. For example, people will pick from certain options about which billing codes that are relevant for the patient. That'll be an example of structured data. But there's actually a lot of unstructured data. And there have been a lot of studies that show that you really get much better performance in terms of predicting things related to your outcomes or billing and anything like that if you also include the unstructured data. Unstructured data would be the notes that may be written by the physician or other healthcare provider. It may be images and tags about those images, or maybe some multimedia, things that aren't labeled in terms of having actual finite number of choices in terms of the field that is being selected. And then the final area is veracity, so basically the quality of the data and kind of where it came from. So there's all this data coming in from different sources. Which sources do you trust? Which sources are accurate at a given time? Does the accuracy change over time? Does some of the data become more obsolete over time? Those are things that are especially important in healthcare because you're dealing with patients where lives are at stake and you may need to make split-second decisions. So what are some of the sources that we can get data from? This shows a few of them, and I'll talk about a couple of them. So we'll talk about sensor data. There's imaging data, whether it be from X-rays, from CT scans, from MRIs. There's database and clinical record information. There's location-based information, which is useful. We'll talk a little bit about that when we talk about a case in tuberculosis where you're tracking that over time. And then there's email, there's clickstream data, social data, web data. And really in big data, what you want to do is kind of put them all together and hopefully have some kind of actionable intelligence. So something that you can do differently in terms of how you treat the patient. And I think this is kind of the paradigm that people look at for big data, but I think the next slide is really a better way to look at it, which is to think of it kind of like a complete cycle, where it kind of refines itself and things are able to adapt to earlier findings. So in this example, we would really start with up here. The circle would really begin here with diagnose and collect samples, and then you're able to do some analysis. You may then map it to certain places. Let's say you have a tumor and you map it to certain places in genomics in the genes to figure out which kind of tumor. Based on that, you may decide to access and find how other people dealt with that data, make it available to them for other doctors, and then to treat based on what you just found. So you want to have actionable intelligence at this point so that you can treat. And then finally, I think this is a really important step that a lot of people are skipping is refining. So put the results back in terms of how the treatment turned out and any new results that you have. Update the databases with new information to complete the loop there. So I think one thing when we think about big data, a lot of people are thinking, just like in this picture about cloud technology, right? And the cloud, where is the cloud? Many times we don't really know where it is. It's in an undisclosed location or it's in some warehouse, and so really there's no way for an individual to really. An individual can access, little parts of the cloud, but it's very much, I think, the same way that maybe mainframes were, maybe a few decades ago, where you kind of have there's a centralized location. Maybe it's distributed. There's a few locations that have some computing power, but you don't have really direct control over that. And so one of the themes that I'm going to talk about here is kind of like the getting analytics kind of for everybody. And so kind of getting it down to the point where there might be an app for it. There may not be an app for snow shoveling, although this year, certainly would have been helpful. But, for big data, we want to have apps so that lots of developers can develop different projects that don't have to deal with all the infrastructure requirements, but just can use the data quickly. So this is kind of how it looks right now, where you have a bunch of servers and at an undisclosed location, and there are very few people who really have the capabilities. Certainly many people in this room do, but many people do not have the capabilities to really use the cloud computing. They may be users of products that use cloud computing, but they can't really use the cloud directly. And so I think one way to kind of analogies back, when, like if you look back about 1,000 years or so, when people didn't have the printing press, or people didn't have ways to mass produce media, then you had, in this case, it was a monk who was copying books by hand. And so people relied on experts to do this type of analysis and this work. And I think in some ways that's kind of similar to what's going on now with the big data analysis, that we're relying on experts to do all of that analysis and then kind of trust that analysis that happens at the end. But I don't know if you recognize him, but this guy kind of changed things about 500 or so years ago. Anyone recognize him? Yes. Okay, I heard. Yeah, I remember. So basically, he changed things by creating the printing press in movable type. It's debatable if he was the first one or not, but the printing press that ended up resulting from that led to mass-produced newspapers, books, and so forth. So really, anyone could really carry a message and have a message of something to say. And really was, in some ways, a precursor to the World Wide Web and blogs where everyone really can say whatever. And so he was actually picked as one of the 100 most influential people of the century. Of the millennium, of the 1,000 years, above Newton and some other individuals. And so what really will take a lot of people do is for large populations to absorb a lot of knowledge and information. And that's kind of what we want to do now with big data, right? To allow a lot of people to be able to integrate that information into their lives in some way that is kind of customized and unique to their experience. And so what I'm going to do in the rest of the talk is really give you 3 different applications that show this kind of approach of using, one kind of using, a couple using an apps-based approach, and one kind of that at least initially needs to use a more centralized approach, but is federated in that there are many different there are many different countries that will participate together and then to form a larger set, and that larger set of information can then be analyzed by all of them. So the first one I'll talk about involves sensors. So if you look, at the watches that are available, the types of phones that are available, there's also, I think here there's an exercise event, like Fitbit and others. There are many types of sensors out there right now. And the thing that's kind of hard to realize is really how much data they're really generating. Some of these are really getting up to big data. So for example, a smartphone can generate over 10 gig of accelerometer data points per day. And a lot of this data needs to be analyzed in real time for it to really be effective if you're going to change someone's behavior or inform them in a way that's actionable. There are other data streams such as a GPS, Wi-Fi, Bluetooth, that of course we're not even taking into account. This just brings up, there's one example that I want to bring up, a company I'm not currently involved with, but I know that these people are, right here from MIT Sloan School, and they have started this company, Health Tech, which basically analyzes this raw smartphone data to be able to accurately tell what a person is doing. So using these accelerometers, they're able to tell, for example, if they're sitting, standing, exercising, and to actually give you real-time interventions to encourage behavioral change. So they have to analyze this big data and quickly make sense of it in terms of their output. So right now, the current model that people have is, let's say, if someone has diabetes or hypertension or obesity, the healthcare provider really offers them a plan. They might give them an exercise plan, or they might say you need to watch which foods you eat. But the problem is that that advice is kind of given in the office, but in the regular setting where they're out in the world, they don't really have many cues to really take the right step. And this is an example of where this app will use big data, combining sensor measurements and other information to actually tell them when, to give them cues on when they should do certain things. So in the new model, basically, the patient does work with healthcare provider to decide on what plan of action is good given their particular disease of interest. But when they're kind of outside the office, there are cues that they get. For example, they may be told by the app to, when they're eating, the app will be able to tell, okay, this is the time when maybe the person's eating, and then they'll get a reminder not to eat certain types of foods. When they can tell if they're in an elevator and they suggest to take the stairs. Things like that are just needed right at a certain time. And that involves analyzing a lot of different measurements all together. So that's kind of an example of one app which really gives people access to big data in a way that they may not even realize it, but it allows them to interact with it. So the next area I want to go into is genomics. So I think, as you saw from the sequence and so forth, like the charts show that genomics is really going to be a game changer really in healthcare. So right now, a few years ago, people were debating about the $1,000 genome, and now it's here. And so essentially, on the order of $1,000, you can get your whole genome. So it's really just a matter of time now before hospitals are already starting to offer genomic sequencing in certain cases, and it's just a matter of now having some of the reimbursement issues resolved, and I'm sure some of you will get to that on the panel. But as we start to gather genomics, what can we do with all that information? So there's genomics of the people, but there's also the genomics of the different infectious organisms. So for example, there's tuberculosis, which we don't many times think about as being important here necessarily, but there are many reservoirs in the developing world where it is developing drug resistance to drugs that which are the top line drugs that we have, as well as second line drugs. And there's some strains that are even completely, totally drug resistant. And so this one project that I have been involved with directly basically involves creating a consortium where you're able to put together a number of different countries, samples from different countries, which individually would not have been enough for analysis, but together provides you enough samples and enough data to do analysis to integrate and to find computationally which different genetic sequences are related to the drug resistance, so we can try and explore and find new drugs for that. And the nice thing is that this kind of approach is kind of generalizable, so you can use it for other bacteria and other organisms as well. So we're just launching now TB resist, tuberculosis resist to make this consortium and putting together samples from a number of different countries around the world to learn about drug-resistant TB and total drug-resistant TB now while we can before it spreads and affects others. So the last kind of overall area I wanted to talk about is really the overall vision of the talk, which is this creation of an app ecosystem as a way to bolster big data informatics, especially in healthcare. And what are some of the things that we'll need to get there? So if you look kind of at healthcare right now, I think the best analogy for it is to think of the electronic medical record kind of like a flip phone. How many of you have a flip phone today? Okay. I think this is the first time not even one person raised their hand. Like, usually we do get one or two people. So obviously something happened, right? I mean, if I would have asked this question like 5 or 7 years ago, I would have gotten a lot more hands in the air, right? So what happened was that there was a problem in that particular approach. So in the flip phones, many times, if you remember back to those days, you had all these vendor-specific apps. Do you remember trying to figure out how the calculator works or the calendar? You could maybe use it on that phone, but you couldn't use it with any other phone, and you couldn't sync it back to your computer. And so really the only way to get information is to actually send yourself an email with that information. And the apps didn't work even with the other apps within the phone, much less with other apps. And the other thing was that there were very few apps because really the vendor who made the phone was making the apps. And their business model wasn't based on the apps. They were trying to sell you phone time. They weren't really trying to have you sell you time where you're playing a game or anything like that. So they'd be rather rudimentary games that were on there. And there weren't really custom specific applications. So there weren't these applications which we would call kind of these long tail applications. That is that there are many applications that actually aren't used by many users, but for those users, they actually could be very important. So an example might be like an app that stores your glucose levels. So for a diabetic, that may be quite important, but most people wouldn't really use that app. On the other hand, if you look at kind of another type of phone, which many of us today probably do have, kind of a smartphone, you see a lot of independent apps. You see the developer and the user community engaged. And you see a lot of these long tail apps available. So how did that happen? Well, the biggest change is that the person who's trying to sell you the number of minutes is kind of different from the person who made the phone and is trying to, and also different from many of the people who are trying to sell you the apps. So there was those different segments were built, and that allowed for all these custom apps to be developed, including ones that are relevant to healthcare. Because let's face it, in some sense, healthcare was a long tail for the people who were making the original flip phones, right? It wasn't something that anyone would really use with regularity. And so now there are a lot more apps that are created for the iPhone. And so that's kind of the vision that our lab and the Center for Biomedical Informatics has for genomic and clinical information. Because right now, the truth is we're really living in this kind of this flip phone world for electronic medical records and genomics. Like you'll have your record on that one system, it won't talk to the other systems. It may not talk to you from the same system within that system. And sometimes people even send themselves an email with like some text that's in the system as a way to get around it, which is obviously not good for user security and other reasons. So, so what we wanted to do was say, can we divide up the space so that you can have apps that do this? So these apps would go into these big data resources. You know, there are millions of records and partners and so forth to be able to do analysis and come up with some conclusions. And could we do something that also supports genomics? So I kind of focused more on the genomics part, and what we really found was that the plugs really didn't fit. Like basically some people would develop certain standards of storing and communicating information, other people had other ones. So if you guys, if any of you have been traveling, I was in China like a month ago, and I ran into this one, actually this was in Korea. After China was in Korea, and I ran into this plug, and it reminded me of the plug in Italy, but it actually turned out to not, it burned electronic if you use the Italian plug. So, you know, it's not just a shape, you have to get the currents and everything right. And so what you really need is an adapter like that is intelligent and figures out what's going on. And that's what we thought is really needed here. So can we make an adapter between all the different types of genomic standards in terms of communicating information? And then once that adapter is made, could it then facilitate the communication and sharing of that information? Because that's what the first step you need to have apps, because you don't want to have an app writer writing 100 different apps for different types of standards. You want to have kind of one operating system, kind of like an iOS or like an Android. And so what we want to do is build basically an API. So you know, there really wasn't a simple API that was developer-centric. But on one hand, the content was very similar between when you talk about communicating sequences and clinical information. Sometimes they're structured a little differently, and there may be different ways to authenticate. So we wanted to capture all of that. And we ended up doing SMART, which is Substitutability in Medical Applications for Useful Technology, a program that the head of the department, Zakwan and Kim Mandel, had developed for clinical information. And what I did was basically work toward developing a genomic part of this so that you could also communicate with genomic pieces of information. And we'll see what that will allow you to do in a minute. So basically, you could write an app one time, and then it would suddenly work with a number of different electronic medical record vendors, because we provide all of the adapters. So that's kind of what we did there. And what we wanted to have is an API, data model, authentication in a standard way, and a user interface that provides a nice experience. And we actually had competitions. There were competitions about writing apps. And these are some of the apps that were written. Then some of the apps were actually integrated into live electronic medical record systems, such as Children's Hospital, where they use a Cerner system. And you know, this was the first app, so it took a little bit longer, about 16 months, but now it should be much faster. And it's now being used every day by physicians. In this case, it's a very simple app. It just takes the blood pressure from, which in this case is from pediatric patients, and translates it back into a scale that the pediatric physician is more used to. So in pediatrics, their blood pressures, in children, their blood pressures are different, need to be recalibrated. And many times the physician will do it in their head, and this one just does it automatically. So it's able to pull all that data and automatically pull it automatically. And that app just took, it took 3 months to code, but I'm going to show you a genomics app that we did that was just really in a couple of months. And so it all works basically seamlessly as an adapter. So you basically have like an adapter around the data source, and then you're able to, with the API, ask for information in your app, and then you can get that, either clinical or genomic information. And what I'm going to show you is one app that was developed that allows you to look at a patient's genetic information, and then it analyzes it for certain patterns, and it tells you if they're at risk for certain types of diseases. So rather than, the approach that people would usually do would be, okay, let's go get the data from the database, do all these queries, and then do some analysis. as a one-time only for that patient. Or maybe build a system that automatically does some queries. But here the goal is, can we have an API so simple that even, in this case, we had a couple of university students, and actually a few weeks ago we were so ambitious we even let some high school students write a couple apps. So they write the apps, and then there's of course a login procedure that the patient or the doctor has to do, so everything's secure. But writing these apps is actually very easy to actually get information, to analyze it and display it from these large databases. And there's sort of different ways that you can do it. So one way you can do it is to create a module, like this Genomics Advisor module, which takes a look at the genetic information, it combines clinical information and drug information, and it displays it. Or you can use that module to be inside of another app, which previously had nothing related to genetics. It was about diabetes and risks associated with diabetes, but did not have, it only analyzed clinical information. But if you put in that module inside, it'll automatically give you information also about the genomic piece of information. So it gives you sort of a nice value added that's very easy to do once one person writes one module. This slide is just to show you that once data is updated in a record, which may be in a database far away, it can also automatically be propagated to the other records and updated so that you always have data that is up to date. And this is just an example of what it might look like. So here would be an electronic medical record, and you have different types of laboratory variables that are measured here, different lab values, and over here, there are charts that show your risks for having certain conditions like hypertension, there's cardiovascular risk, diabetes type risk, and also drug risks associated with having certain types of drugs given your genotype information. And this was just automatically added as a module onto the overall diabetes program once that app was written. Where you can get more details. People in China have been really interested in this, and this is, if you can't read it, it's because it's in Chinese, literally. But it really contains the same information. And they're really interested in getting this to work with their systems, which have a lot of more centralized data, including many millions of patients together. So the last step I want to tell you about is sort of how can you integrate the notion of healthcare, sensor data, big data, analytics, in a way that's more consumer friendly. We showed you one example before, which was related to predictive analytics to help people in managing behavior change. In this case, it basically is about diabetes compliance. So when someone is in, let's say, in a pediatric case, you have a young child and they have diabetes, let's say diabetes type 1, then they, as a child, they may not know and really have much motivation to have measurements of their glucose, to exercise at the right point, to control their portion sizes and so forth. And so what this app does is it interacts with them through something that they know best, which is toys. And this is actually a commercial toy that's made by a local company here where the goal of the toy is really to actually teach children about diabetes and what it means to measure their glucose risks and things like that. And what we've done is added on top of that a glucose monitoring device, as well as an app which links up to all this sensor data. So basically, we decided to use an iPad because we needed more screen real estate. And so you can actually get this app right now. It's on the iTunes store. I think type in DBEMR for diabetes electronic medical record, and it's actually the first program that integrates genomic device sensor data and electronic medical record information. And what it does is in a very user-friendly way. Here we see someone kind of downloading that app and running that app. You'll get to the first screen where the goal is really to kind of bring this data analysis and everything to the masses, kind of like discussion, or the topic of the conference, and bringing analytics to the 99%. So all of the analysis is kind of presented here, and different screens are for the different individuals that are going to be in this healthcare encounter. So the child is going to be there at the doctor visit, the doctor is going to be there, the caregiver, the parent is going to be there. And each of them can look at the screen, and each has a different piece of the screen that's really geared toward them. And really on this kind of flat surface, it really is kind of a level playing field that they can all see everything together. So this part is taken from the medical record. And if you remember before, there were a couple screens that you saw some of this information there. It has their diagnoses, medications, and some variables that may not be that relevant or of interest to the parent or the child, but the doctor will see that. And then there's some information that may be relevant to the parent to see how well they've encouraged their child to do measurements for glucose. This is the glucose measurements, average, minimum, and maximum over a number of days that's automatically uploaded to the cloud from the device that's attached to the bear, the toy bear. Meanwhile, down here, we have their genetic risk, which was assessed by taking a saliva swab, and that tells them their overall risk over time to develop different conditions, and really is a factor that, in combination with how well they can control their diabetes, will affect their trajectory in terms of how their disease will progress over time. So these pieces of information are for really interpretation by the doctor with the patient. And then kind of the thing that's a little unique is that we provide also an avatar, like a representation of the bear that the child is usually used to seeing, which is their toy bear, in the doctor's office setting. So usually the child, in the past, they would go to the doctor's office, they're sitting in the corner, the parent is having a conversation about something that the child doesn't understand, and then they go home and the child is given basically some orders of what to do, but it doesn't really make sense. So the goal here is to really bring the child into the picture. The child has been playing with the bear. The bear, can signal if it, can signal essentially if it's happy or sad. So, for example, there you can see it's sad because the child's measurements over the recent few times have been rather high in terms of the glucose. So the bear is going to be sad and communicate that. So really turning the data into something that people can understand, I think that's kind of what I wanted to show you in this last example. So there's a lot of different populations you could aim for, right? You can aim for the physician in health informatics. You can aim for the caregiver in health informatics, the helicopter parent, right? You can aim for the child within the context of a physician or other healthcare provider being present, or you can have something that interacts with the child on a daily basis, because the healthcare provider isn't going to always be there. But it certainly is useful to reinforce it through things like this avatar. So, so the bear can be happy or sad. You can get more information about the genomics. And what I wanted to point out here is that this is actually, again, that module that one person had written, who had no idea about the bear, about the other part of the app. What they wrote about was basically how to interface with our API, to get genetic information. Wrote that in a few weeks, and then someone else could automatically integrate that here. So I feel like in the future, for big data to really reach all these nice target audiences, like a good way to think about things is by building these modules that are really going to be interacting with other modules. So that's kind of where apps kind of come in. Like you have a lot of apps that can have modules inside them, and the apps can interact with different types of individuals who would use them at different times. Some of these apps may be running in the background, communicating with other apps. By doing it in that way, you can allow people who are specialists in that type of technology to abstract away that piece of information that's the hard part, which is how do I connect and get that genetic information? How do I display it in a meaningful way? And yet allow that information to be used by other apps which might just need it to use that information at a higher level of abstraction. So that's kind of, I think, the key point that apps would allow us to do and get us away from the flip phone and really toward a smartphone or a smart health informatics kind of approach. So with that, I think we're running low on time, so just If you guys, I think we may have time for a few questions, but in case you're too shy or you don't catch me later during the food session, here's my website and email, or you can check my Harvard site as well. With that, I think I'd like to thank you guys and also to open up for any questions.
Thank you, Jill, for that very interesting presentation, and anybody has any questions?
Great talk, thank you very much. I have a question about the integration of data from a large hospital system into clinical practice. So the collection of data is one thing, but once you start integrating their data streams and they accumulate technology history as well as different vendor streams, it invariably turns out it's very hard to integrate data. So for instance, risk beliefs could be present on one chip platform and absent on the other, or interpolated from another platform, and that may be done incorrectly or poorly, like low fidelity. How do you capture that in clinical practice and abstract it to the point that the doctor doesn't have to worry about that?
Right. So, good question. Now, are you specifically referring to clinical information or genetic information, or kind of both?
I'm specifically referring to high throughput type or high tech, more data, for instance, MRI data, genomic data, any kind of data where the platforms from which it's collected evolve and are subject to patch and platform biases.
Right. Yeah, so that's an issue that's been with us probably since the beginning of medicine. It's just that now it's getting to the point where it's really hard for an individual to sort of curate each piece of information. So there's really been a couple of different approaches to that. One is to have basically kind of a back-end curator, someone who is curating the pieces of information. That's kind of expensive. One of the approaches that some people have been thinking about now is more like a peer review kind of system, almost like a crowdsourcing, but not to the general crowd, but more to a crowd of people who have patients in common or have a specific expertise in that area, and they have some reason why they might want to review this, because if they review someone else will review for them, and so forth. So that's another approach. And then, of course, there's just the approach of give them everything and hope they interpret well. So you can say like, okay, well, we don't have this interpretation, or we have an ambiguous interpretation here. You make sense of it. And different doctors really prefer different approaches. Some people, they don't want to know what the current state-of-the-art interpretation is, because they have their own interpretation of what approach you should use. Just like, people can prescribe off-label drug use, right? Sometimes people will have a certain use that they think will be the best way for their patient. So we found that having, and actually that's in kind of this slide, kind of skipped over a little bit, but see, like, this is a slide that most of the physicians would be happy with, but then they have this pop-up that comes in which gives them all the detailed information of where that data came from if they want that information. So I would say that the best is to try and summarize it, but then for those who want all the information, have a way for them to see that, and where it clearly says where the ambiguities are. Oh, question?
Quick question. Great presentation. Wanted to hear your thoughts more on the unstructured text and how it's being employed, and what other use cases do you think it has added more value compared to just using the codified data?
Right. So I'll repeat the question in case people back in here. So it sounds like the question is basically about the nature of structured versus unstructured data. How would structured data, or how would unstructured data be useful in healthcare specifically, perhaps? So we actually know most of the information is actually in the unstructured text. Like, people will, and the reasons are because people only will use the structured fields for things that they have to do. Like, they have to put in billing codes so they can be paid. And that actually biases their choices. So they may put in more billing codes. In fact, if people are paid to be coders to try and maximize the bill by optimizing the codes that are selected. So it may not actually relate to the diagnosis per se. And there may not be uniformity even within a hospital. So it's a little hard to trust the structured data. The unstructured, I think that in some ways is more, people have shown also that it's very useful because there the physician kind of has the opposite incentive. Like they want to kind of, in an optimal way, write down as few words as possible to finish the notes so they can go on to the next patient. So they want to optimally capture information. So they'll use shorthand, which is hard to interpret, but presents a lot of interesting challenges. And they may refer to different patients, which makes them essentially not anonymous. Like they may say, well, let's say the note says, well, the mayor of the town came in today. It doesn't have their name, but anyone reading that would be able to identify who they are. So it presents a lot of big data challenges to try and figure out what makes something secure, not when you're analyzing that, what to release, what other things. People have shown that if you use unstructured and structured versus just structured, unstructured really improves predictive accuracy a lot. And I think it is for those reasons that I mentioned. So I think even though it's a lot more messy to deal with unstructured data, the approach that people are now taking is let's try and make a gold standard for how can we map unstructured data into something that some people accept to be is more structured. So that's kind of more intermediate approach. And then other people are trying to use like curation, which is like individuals will read that text and try and assign it to different categories. And then finally, we've got these automated methods, which aren't perfect yet, or you never will be, but they can be compared against some of the gold standards to at least, and then double checked on by humans. But it makes it much faster than just doing an analysis just by each person reading all the notes. Oh, question.
Hi, in your experience, are different institutions willing to pool their data so that there's a larger pool of base data of certain disease conditions and so on, or is that more or less disease specific?
Yeah, that's a good question. So it really, at this point, in terms of pooling data, so you're going to relate to the TB consortium, I think, part, which is like, if you have different samples in different places, how can you pull them together? I found that it has been more investigator level, like at the level of individual research scientists or department heads, like more at a kind of a personal, even relationship level, like that. You know people at the conference, and it's like, oh, I've got a few samples, you have a few samples. Wouldn't it make sense if we analyze them together, because then we'll have enough power to make a statistical prediction? Whereas before, even though we had a lot of data, we didn't have enough samples to make a statistically powerful prediction. So having said that, there are sometimes government initiatives that encourage people to work together by giving grants and things like that that are international. So I was funded one a few years back by a grant that both the NIH and the corresponding institution from China both announced that grant, that the only way to get that grant is if you found a collaborator in the other country and you both turned in the same proposal to work together. And they would only consider proposals like that. So we found a partner over in Shanghai, put together that proposal, and we were able to share samples and share data, right, based on the types of work that we needed to do and get a lot more statistical power. So I think it's more at the investigator level. Would it be nice to have it more at a level of institutions? I think it would be. And there are a few things like that that are emerging. In fact, there's a network called eMERGE, which is about combining electronic medical record data for research at this point across different centers. And so then you can look across different diseases. And those are being formed more at the institutional level. So there are some things like that that are starting.
And just to add a little bit on that, there definitely is the hardware initiatives which help with that sort of a process. NIH has a Center Without Walls initiative, which really promotes that cross-country or cross-institutional collaboration.
Hi, you laid out a great vision. I have a question about your thoughts for the regulatory issues. Because, big data can give us a lot of correlations, but then actually using it, you need to prove that it's clinically relevant, like the slide you had on the genomic advisor. And we've been following up, the FDA, 23andMe interaction. So obviously it's a big issue because it's a heavily regulated space. So how do you plan to, what are your thoughts about using this data effectively?
So is your question, wait, so can you, I didn't hear the very beginning of your question?
I'll give you an example. Big data can help you find a lot of correlations, like alcohol consumption can be correlated with lung cancer. But in fact, the issue is that people who drink usually also smoke, so it's actually smoking that causes lung cancer. So big data can give you a lot of correlations, but maybe most of them are irrelevant, and you really need to find the one that's relevant. And to do that, you need to run clinical trials. So you can't just take all this data and generate conclusions or guidelines without really testing it, right? And it's the testing that is the problem, like following up on all these things.
Right. So there are a lot of new efforts now in that area. One of them is ClinVar, which is a database of variants which have been found to be clinically found to be significant. And then there's a rating basically about what level of significance and how well they're trusted. But it's an evolving area. So we have a way to get into that data, and then basically through an API be able to read in which ones, and then provide kind of quality information based on that. There are, for those who do want to do those trials, that is another avenue to pursue. We've been doing that for, but it's very hard to do that for everything, right? We've done like specific things like related to TB, tuberculosis, but in terms of like providing information about risks and things like that, like we have to rely on whatever is known based on publications and or clinical laboratories that are putting in information into the database and provide that kind of rating about if it's been validated or not, or if it's only suspected. So yeah, it's a good point, and I think whenever you have a new technology, that's kind of what happens. You don't really know everything, but you want to be able to give something, and so you kind of have to qualify it in some way by giving those ratings and links back to the original source.
I have time for perhaps one more question.
There's one in the front.
So I'd like to ask you a question about the big data and the legal aspect. And for genomic data, they are personal and they are currently legal law has not really governed how to protect the data yet. And how will the data analytics going to use the publicly available data, or is there such things for some of creativity that we can put together to help our age? So if you have an idea and you want to pursue, and how do you get the sample data without jump through the hoops and go through the clinical trial or go through the investigator union to get the data? Is there a good way to get the publicly available data?
Right. Yeah, good question. I think that's actually kind of one of the goals in this talk, and is to show that with these apps, really anyone can do this. So like, these apps that are just, Genomics Advisor and DBMR, those are all apps you can download right now on, an iTunes store. And the API, the programming, the code for these programs, for the Genomic Advisor, the API, it's all public, Apache license. You can just, basically it's free to do whatever you want. And so what that allows you to do is actually get data from places like 23andMe. They have some demo data that you can get automatically, or you can use your own data. Or if other people give you their password, you could use their data. I mean, we're not going to deal with the security things. We allow you to log in if you have the authentication to get that data. There are many sources of public data also. So one that comes to mind is like GEO, the Gene Expression Omnibus, that NIH has that's freely available, downloadable data that an app like this could easily interface with that piece of information. There is dbGaP, which you do have to apply for to get, but it's free and if you apply for it. And so having a standard like this, it basically means that you can abstract away all of the parts of how to read in the data and things like that, and you can worry more about what are the predictive algorithms you want to use, how do you want to integrate it with any clinical information we have locally, or any sensor information that's coming in, things like that. Yeah, good question.
Thank you very much, Gil.